So welcome to SciNet, and this is the intro to SciNet and using Niagara and Mist. My name is Ramses van Zon. I'm, as I said, one of the analysts here. My background is in physics, chemical physics, theoretical physics, and molecular dynamic simulations, and that's how I rolled into a job like this. So what we try to cover in these intros is a little bit about SciNet, so that you know who we are and why we're here, and what you can get out of us. And then we'll focus on how to use our systems. So we have two main systems right now, Niagara and Mist. So I'll tell a little bit about them and how to use them. I also like to throw in some data management and I/O tips, because those are the things that you don't think about beforehand that will eventually become a bottleneck. And so I end with that. But the main part will be using the systems, but it is nice to know who we are. So we are SciNet. We are located here at the University of Toronto. We're officially a consortium of the university and the research hospitals around us. What we do, or our primary mission, is to run and support users on massive parallel computers, so large-scale computations for any researcher, any academic researcher in Canada. So our systems aren't just for U of T and the hospitals, they're for anybody in Canada. We're not the only such consortia. There's about 5 of them throughout Canada. Some of them also have systems and provide services. And so depending on your needs, you might run on our SciNet system, so Niagara or Mist, or on one of the other systems if that's more suitable for you. Together, we all make up the Compute Canada family, although that name will change in the near future. So throughout Canada, academic resources, there are a couple. There's 3 so-called general purpose clusters where you can run. They are heterogeneous in the sense that they have many different configurations, some nodes with GPUs, with different kinds of GPUs, different memory sizes, different processors. And so they're for almost any kind of job. There's 3 of them, Cedar, Graham, and Beluga. Beluga is the latest one and has slightly newer architecture, but those are not going to be the main focus of this talk. The main focus is on our 2 clusters. One is the large, we call it large parallel cluster, so Niagara. It's set up for larger jobs, so jobs that can use several cores at the same time or just need a lot of resources. And what's kind of almost easier in this case, as you will see, I hope, is that this cluster isn't heterogeneous. Every node is the same. Asking for resources is basically a single number. How many nodes do you want and how long do you want them for? And the rest is up to you. So it's kind of simpler to schedule and to understand in that sense. But you get big chunks at a time, and so you have to use them. The latest cluster we have is a relatively small GPU cluster, but it's of a different architecture than any of the other systems, and I'll go into what that means. And it's kind of the small GPU sibling of Niagara. Niagara doesn't have any GPUs whatsoever, and surprisingly, that works very well for a lot of use cases. But for those that it doesn't, we now have Mist. In addition to these sort of pure compute systems, so these are systems where you have a computation to do, you know what program you want to run, or maybe even develop it on those systems, and you write a little job script and you run it, and eventually, or you submit it and eventually it runs. That's really for mostly compute-based workflows. There's also a few cloud systems in this sort of network of resources, where you could host a website or a service or something like that, which works very differently. Again, like that's a whole different ball game. But there's several cloud systems that are available if that's something that your group needs. If you have access to Niagara, you automatically have access to Mist, and because it goes through a Compute Canada account, you also automatically have access to Cedar, Graham, and Beluga. The cloud you would have to request separately because you'd have to set up a VM and all of that. It is very different. Vice versa is almost the same. If you have access to Cedar, Graham, and Beluga, you can get access to Niagara with the same account, but that access has to be activated. And I have a little slide showing how that goes. But the idea is that anybody that has a Compute Canada account can use it for all of these cases. We have one of the fastest supercomputers in Canada, Niagara. It just got updated to have over 80,000 cores, and it's running fairly smoothly. And they have a bunch of other smaller ones, the Mist GPU cluster, an older GPU cluster from the SOSIP organization. We have a Teach cluster, which is mainly used by profs at U of T. We also have a longer-term storage facility. It's called HPSS, High Performance Storage System, which is basically a tape-backed system where you can store data for a longer time. It takes longer to retrieve it, but it doesn't take any room on your on disk. So that's useful. So that's kind of what we have in terms of systems. So we maintain this, we support these, but we also do some other stuff. We also do a lot of training, because these clusters are a little bit different from your regular workstation or laptop. There are some classes, quite a few classes we give. We give this intro here. We have classes in scientific computing. We have courses on data analysis, biostatistics. We do summer schools in the summer. Those are week-long events where usually have 3 streams, maybe more, of data science, scientific computing, parallel programming. You can pick and choose your poison. So this goes on throughout the year and in the summer. If you want to see the full list of courses that you can take, go to courses.scinet.utoronto.ca. You can log in with your Compute Canada account just like anywhere else. We do some research. A lot of it has focused. Some of it focuses on the pedagogy of doing this training. Others are come out of collaborations that we do with our users. So if you're interested, I have the link right there. And then these are our people. It's a relatively small group, kind of arbitrarily cut up into a user support analyst section on the left and a sysadmin section on the right. There's a lot of crossover between these two. We don't make this distinction too strictly, but it means that most likely if you're emailing with somebody, it'll be somebody from the left side. But then don't be surprised if some of the other guys type in going, oh yes, I am a sysadmin now, but I know everything about molecular dynamic simulations, and it will help you out. This happens as well. If you have any questions, any problems, the most direct line to all of these folks is support@scinet.utoronto.ca. There's a Compute Canada helpline as well, support@computecanada.ca, which will eventually also get to us. This one seems to be a little bit better monitored, so probably the most direct line for you. Okay, so let's look at the two systems in detail. It'll also show the differences a little bit before we look at how to use them. So this is Niagara. As I said, we just upgraded it to 80,640 cores. Those 80,000 cores come in batches of 40 cores each. So there's what we call nodes. A single node is a multi-core machine with 40 cores, and then there's about 2,000 of those. And so that's what supercomputers are these days. You take beefy workstations, very beefy in this case, 40 cores, and then 2,000 of them, and you network them together, and you make a supercomputer. And so each of the nodes, in a lot of cases, you might just be running on a single node, and that is fine. But then it's good to know what those nodes are. Those nodes have 40 cores. We have 2 generations, but are very similar, of Intel chips in them, Skylake, Cascade Lake, but it doesn't really matter too much. We found in practice. You have about 4 gigabytes per core. So that's per node. There's a list of the top 500 fastest supercomputers in the world that's being maintained. We were at number 76 on there, so we're in the top 100. That's always nice to know that you have something worthwhile having. That's based on the single run of the whole system. Nobody does that. This is a shared system. There's a few hundred users at any given moment running stuff on it. And that means we actually have a mix of different size jobs. Some are really large, a few thousand cores or more. And some are just using 40 cores on a node and are very happy doing a lot of those simulations. And that's fine as well. We run Linux. Almost all supercomputer clusters do that. So if you're not familiar with that, we have courses in Linux, so look up the courses and get yourself a little bit trained. The interconnect, that's the thing that connects all these nodes, is one of the things that really sets this apart and makes this a supercomputer. The specifics are that it's an InfiniBand with a Dragonfly Plus. That doesn't really matter. What matters, it's really fast to get data from one node to another so that you can run jobs that span nodes. And that's the point of that. In addition to having the nodes, the interconnects, you need storage. And so we have a shared file system. Shared means all the nodes see the same file system. So once you have your files on this file system, you can see it from any node of Niagara. You don't have to ship anything back and forth. It's also possible to write to the file system from different nodes at the same time, and it's all sort of coordinated. So that's nice. On the other hand, it also means that the file system is used by all the nodes. So it is potentially possible that the file system is sometimes a little slower because of people are doing a lot of reading or writing from it. It hasn't been a real bottleneck yet, but it can be. The most bottleneck you would probably find is if you yourself write to the same directory for many jobs at the same time. So it's fairly easy to trip over your own feet, but that you can solve. But anyways, the fact that it is shared does mean that we need all of the users to be sort of responsible in how they use the file I/O, because it does affect other people. If this file system, these shared file systems for home and Scratch Your Project are not fast enough for you, we also have a somewhat faster file system that's smaller and not backed up. It's called the burst buffer, but that is a specialized bit of I/O for those people that really need high read-write. Mist is a lot smaller. It's I like to call it Niagara's little sibling. It's not even all a national system. About 70% of it is actually a SOCIP system. SOCIP is an organization that administers and gives resources to projects that collaborate, that are collaborations between academics and, say, small and medium enterprise businesses, startups, that kind of stuff, which is very interesting. And they were looking for a replacement of their GPU system, and we said we also don't have a GPU system. Let's put our resources together and create one larger GPU system. So in the end, what we ended up getting are 54 nodes, so a lot less nodes, but each node has 4 GPUs. So in total, that's about 200 and something GPUs. And those are the latest GPUs. They have a nice connection between the different GPUs. The nodes themselves are an IBM architecture, which is a slight issue in terms of software. Any software that works on Niagara has to be reinstalled on Mist to work there as well. But we take care of most of that anyway. So the way that you work with GPUs, though, most of the time, if you have a GPU code, a code that really can use a GPU, it almost doesn't matter what it's doing on the CPU side. So it's not that big a deal. But the nodes are of this power architecture. They have a fair bit of RAM, and then the 4 GPUs, as I said. Most of the computational power comes from these GPUs. The theoretical highest performance that I listed here, 1.6 petaflops, is all just the GPUs. The CPUs almost do not count in this sense. It also means that if you have a code that doesn't use GPUs at all, there's no point running on Mist. Like, there's fewer nodes. Maybe it runs like a few % faster, but you have way more resources in Niagara. So if it's a CPU-bound code and it doesn't do much GPU, just forget about the GPU, run on Niagara and run at scale. But yeah, if you do have those GPU codes, this is where you can run them. The interconnect is the same as Niagara, the operating system is the same, and the file system is the same. So it could be that you have some data that you generated I don't know, through simulations on Niagara, and then you run them through some neural net machine learning algorithm on Mist, and that's fine. The data doesn't have to be moved. It's already where it is. So you could use both of them with the same data. So that's Mist. Now, if you want to get access to these, as I said, you have to get your Compute Canada account, but you also have to get this extra activation. And basically that is for a couple of reasons, but mostly it makes it easier to put you in the scheduler and to get some disk space. And so once you've gotten this, and I think most of you already have your Computer Canada account, you go to this opt-in service link and you click on the join button. You join Niagara and Mist. Sounds very friendly. It is. And then within a few days, sometimes if it's the same business day, you get an email saying, welcome, and go connect to Niagara. So after that, after you've opted in, it's just that Computer Canada account that you need to do this. Does that make sense? Okay, so suppose you have an account. How do you log in? Now, all of these compute clusters do this the same way. They use a utility called Secure Shell, SSH, which on Linux and Mac is pretty much standard. On Windows, less so, but you can download a utility for it, like MobaXterm or the good old PuTTY. And then that will give you a terminal. So most of the interaction with the system will go through a terminal, so the command line. It's very rare for people to use GUIs for running at large scale. It's just less reproducible. In any case, this is what you do. You open your terminal, you type the command SSH -y is for getting graphics back on your system if you need it. You might not need it. And then your username, and then add niagara.computercanada.ca. The alias niagara.scinet.utoronto.ca also works if you've been using that. There's no need to stop. And that gets you into Niagara, but it doesn't get you on one of those 2,000 nodes. It gets you onto what we call a login node. So the login node is where everybody logs in. There's multiple users on that node. You can compile your code there if it needs to be compiled. You can download your code. Otherwise, you can edit it. You can prepare your jobs, a job submission script. But there's in total for Niagara 6 login nodes with a few hundred users. That's still dozens of users on one node. This is not where you want to run because you don't know how long things will take. You want to run on those other nodes, those other 2,000 nodes. And so we have a strict way of getting access to those nodes, and that's purely by a batch queue. So you'll have batch jobs that need a little script. We'll show you an example of the script in a second. You give it to what we call the scheduler. It goes into a queue. When it's your turn, it will run on one of the compute nodes, or if you needed more nodes, on several of the compute nodes. It works the same with Mist, except Mist is called Mist and not Niagara. That's the only difference. Okay. Have you guys worked with SSH before? Yeah. Okay. So this is not you haven't? Okay. So are you on a Windows machine typically, or? Okay. So just open the terminal, type SSH, and you're in. Yeah. Okay. Perfect. Okay. So you're in. Where's your stuff? So you have a couple of directories. It's a shared system, as I said. So there's a few directories that are yours, lots of directories that are not yours, that you either don't have read or don't have write access to. But the ones that are yours are two main ones: the home directory, which is very common in all Linux and Mac systems, and the scratch directory. So your home directory will be where you land initially when you log in. And it will look something like /home, /a letter, /a group name, /your username. So depending on what your primary group is, that's where you will live. And then, which is great, the home directory, you have up to 100 gig there. It's backed up. It's good. But 100 gig is not that much when you're dealing with large-scale computations. So there's another area called Scratch where you have a much larger leeway. The only thing with Scratch is, as it kind of indicates by its name, is it's not backed up. It's meant for temporary data. So the model here is that you log in, you write your code, you run it from Scratch. It writes to Scratch, and then whatever is valuable enough for you to keep, because oftentimes there's like intermediate time points or iterations. You don't need them. You copy them over those parts that you need either to home if it fits, or to your own local machine if that doesn't fit, or if you need it to store longer, you can request what we call project space. But we'll get to that in a second. But the idea is prepare on home, run on Scratch, and then Scratch will get purged every 2 months. So you have basically 2 months to do your post-processing on whatever you created, or and then it's up to you what you do with it afterwards. Just to make it a little easier to get around, we have defined a home directory variable, so home and $scratch. Use these variables. If you use these, your scripts will have a better likelihood of working on the other systems as well, where your location might be different, but there's still a $home and a $scratch. So use these variables. As I said, if you have data that needs to be kept there for more than 2 months, so it's inactive for that, you might want to get project space. And now, different from the general purpose machines, project space is allocated in Niagara. That means if you don't have made a request for it, you have none. How do you request? There's 2 ways. If you need a tiny bit, ask us and we'll give it to you. So think of a terabyte at most, maybe 2. If you need anything else, because space is limited and this is backed up and tape space is also limited, you have to go through what's called a RAC allocation round. So RAC allocations, resource allocations, are a competition that happen every year. The call goes out in the fall. You ask for a certain number of computes, a certain amount of storage. That goes through a bunch of committees. They decide who gets what. You get to hear that in March, and then April 1st, you have your storage and you have your compute. So that you need that for larger scale things. For smaller scales, you're probably fine with what you have without that. And then there's a burst buffer. As I said earlier, if you have heavy I/O computations, you can request some space on the burst buffer. And again, all of these are in project and in environment variables, so it's fairly easy to find. So your main ones are still going to be home and Scratch. Even if you have project, you're going to run on Scratch and copy over to project what is valuable. That way, you don't waste space on project that you don't need. Okay. I'm going to skip this, but this also explains what exactly the purpose is of each of them, but I kind of went over it. An alternative to having this fast I/O, if it's temporary data, is sometimes to work with what's called a RAM disk. So if you have many temporary files that are created and deleted during the computation, but you don't need to keep them, putting them on a shared file system is just unnecessarily slow. Putting them in RAM, so in memory, is faster. So it speeds up your code and it doesn't hurt the file system. Good stuff. Some limits here. Home has 100 gigabytes. What I didn't put in here, although I should have, is that there's also a limit on the number of files. And I think it's 250,000 now. And the reason for the limit of the number of files, a few reasons. First, many files don't work well on the shared file system. It also makes the backup slower. And so we just put a limit on. 250,000 seems like enough. For Scratch, the limits are a bit higher. Project, again, would be higher, but it depends on your allocation. The other thing that's important for Scratch, but I mentioned already, is there's an expiration. If you haven't used your data for 2 months, it gets put on a list. You get the list, and the list says this will be deleted if you don't do anything. So you get a 2 months notice, a 2 weeks notice for this. Yeah, and what determines the 2 months is not when you created the file, but when you last used it. So if you even opened the file for reading, that still counts as being an active file. That is not going to go on the list. That won't be deleted. So active databases and stuff like that, you can just keep it on Scratch and it's fine.
For example, like a data set system for Scratch solutions, read every time.
No, yeah. It's Scratch, but it's for active files basically.
Right.
Yeah,
so
that's,
you're not going to delete something that's like
no.
When you have that.
The last thing that I'll just mention briefly, because again this goes by allocation, is archive. This is our HPSS. This is going through a lot of different names. HPSS is what we've always called it because we've had it for a while. It's kind of like an archive space, but this is starting to be called nearline in the larger context. It's tape-backed storage. If you have something that lives on Scratch, say, or even off project, but you don't need it for, say, a half year or maybe a year, store it on the archive, and retrieve it when you need it. It doesn't have to be on spinning disk. And there's way more storage space available on that than in any other systems, as you might understand. Backup, also, I should stress this, doesn't mean that you can ask for your file as it was like half a year ago. We don't do versioning. We do a latest copy. So if you accidentally delete a directory and you email us right away, we will be able to get it back. If you accidentally delete a directory and you wait 2 weeks, okay, can I get it back? Well, we don't have that anymore. So it's a latest copy, kind of a latest snapshot kind of backup. That's all it is. Okay, so that's where you can put stuff. How do you put stuff there? Moving data. If it's not too much data, a couple dozen gigabytes, just copy them through the login node. So remember, you logged in through Niagara.computercanada.ca. You can use another utility called scopy or rsync, WinSCP in Windows. They all work to just directly copy and using the same address. The reason that for much larger things that won't work is that copying isn't entirely free. There's some computation, and there's a timeout that will basically cut you off. So what do you do if you have more than that? There's 2 things you can do. You can go through dedicated data mover nodes, data mover 1 and data mover 2. Again, you can directly access them from the outside to copy things in. And they even have a faster connection to the outside world as well, so it tends to be faster and not time out. But you still have to sort of be logged in and sort of monitor it, and if it breaks, you have to try it again. So if you're trying to do this over Wi-Fi, this can still take a long time, right? There's another service if you're doing a lot of motion of data often called Globus. It's not something we created, something that we offer that we have as a service. It's a web-based tool. It involves setting up a separate account and then logging into where you want to copy from and where you want to copy to. But the nice thing is, once you've set it up and you said, I want to copy A to B, and you say click go, you can close the browser and you can forget about it, and in the background it will keep doing it. If something goes wrong, it will retry it for up to 3 times. It can either be compressed or not compressed. It can be encrypted or not encrypted. It has a lot of features. Because there's some setup initially, I would recommend that if you do it often, if you do it just once, just copy it over and be done with it. And then HPC is its own thing. So if you ever need that, just look up the documentation for that. But it's its own thing. All right, so that's storage space, how you get your data there, how we log in. Now you want to do something with the data. You want to run an application. So software and maybe libraries. So you're on the login node. What can we use? Can we just start using this? What is installed? And here the fact that this is a shared system really shows itself. We can't possibly install all software that people want for their research, because oftentimes software packages conflict with one another, and so what Group A might need cannot be installed because what Group B had needed is already installed, etc. So there's a perfectly reasonable way around this, but the way it will look when you log in is as if there's no software, like almost nothing is there. You have to enable the software that is installed through a module command. So there's a module system. Basically, all software that people have asked to be installed, or that we found useful, has been put in modules that you can load. You can pick and choose which ones you want. And this way, we can offer different versions of the same package. We can offer conflicting versions, because all that people have to do is not load those modules at the same time, and it's fine. It also doesn't really install the software. Software is already installed somewhere. It just tells the operating system where that somewhere is. And so it really just sets a bunch of environment variables like paths and LD library paths and etc. And so if you want to know what software there is, you have to use these module commands. And the first thing you will try is a command called module spider. Spider goes through the whole tree of installed modules and shows you what they are. So it will look something like this. You've logged in, you type module spider, you get a long list. It's kind of too long, really, alphabetically ordered of all possible modules and their versions. If you see the one you want, you go, okay, well, now I want to load it. What do I do? you use the module load command. So module load and then the module name, often a name / a version, makes it now loaded, and you can use that software. If you want to start from scratch, you can purge all of the previous loaded ones, module purge. If you want to find something, the module spider command gives you the full list. If you want to know all the versions of a specific module, you can do module spider module name. So if you wanted to run, say, GrowMax, you can do module spider GrowMax, and it goes look for GrowMax in the module system. Now, because there's conflicting packages and some packages needs other packages, the modules are actually organized in a tree. So there are some packages that are installed with, they're compiled with, say, the GNU compilers, and others with the Intel compilers, and they're not compatible. There's two branches of that tree, one for GCC compiled stuff and Intel compiled stuff. This hierarchy makes it a little harder to find things. And so there's two commands. There's a module spider that tries to go through that tree and find everything for you. But also module avail, which will only show you those things that you can load right now, those modules that you can load right now. So for instance, if I had a GrowMax that is installed with GNU compilers, if I don't load the GNU compilers, I cannot load the GrowMax. So I have to do it in sequence. I'll show you an example in a second. Finally, module list just shows you what's listed, what's loaded right now. So to make things slightly more complex, there's not just one tree. There's actually a bunch of trees. There's a forest. Two main branches. One is the original software stack on Niagara. We compiled it. We made sure it's optimized for this system. And that's the one that you have by default. It's called NiaGANV. We're building NiaGANV 2020 right now. But NiaGANV 2019b is probably your best bet. So you can load that. But that's not the same software stack as they have on the general purpose clusters. And sometimes people want to take what they ran on the general purpose clusters and run it on Niagara. And it is possible for the most part. And so you'd have to switch trees, essentially. And this is how you do it. You do module load, CCN for compute Canada environment. And then in those other systems, not only do you have a different stack, you also have a couple of modules loaded by default. We don't like that particularly because at some point you want different modules and you're going to unload things before you load them. But if you want exactly the same environment, what you load is not just the CCNV, which switches you to that stack, but also STDNV, which is the standard environment that they would normally have. And in that case, you can do whatever you were doing on Cedar, Graham, and Beluga on Niagara as well. So if what you need is in the default stack, you don't have to do any of this. You can forget about the right side and you just focus on the left side. So suppose that that's what we want. Oh, and on Mist, we have yet another stack, but that is because it's a different architecture. But it works the same way. The module commands are the same. So few more tips that are important, especially if you're going to do things on Mist and Niagara. Don't load modules in your .bashrc. If you know what the .bashrc is, it's the file that gets started when you start the shell. So when you log in, that is one place. And you might go, well, I always want the same modules, I think. So I'm going to put these module load commands in my bashrc, and then when I log in, I don't have to load them. And it sounds very convenient, but then you SSH to Mist and try to run somewhere there, and your bashrc is trying to load Niagara modules, and it just won't work. Or at some point, you want to run a code that needs a different module, and you get all kinds of, hopefully, just warning messages or conflicts, and your job crashes because it has the wrong modules. So the best thing is to not start with that at all. Don't leave your bashrc nice and clean. If you have to load modules, load it in a script, load it in your job script, load it on a command line, put it in a separate script if you need to. There are some handy ways to do this. Putting it in your .bashrc is not the best way. Give specific versions as well. You can just load the Intel compiler by saying module load Intel, and you probably get the latest one, which is nice to start with. But for reproducibility, when you're running your code, put in exactly what version you have. It's just a record for this ran with that version. If you ever install a new version, your job is entirely reproducible, and you can resubmit it. Say you hear back from the paper reviewer, and he said, run this again. You can run it exactly the same way. And then there's the dependencies. And let me just show how the dependencies work by using module spider. So suppose I want to load a module called OpenMPI. It exists. And I do module load OpenMPI, and the module command starts complaining. Now, the module command calls itself lmod, and so lmod has detected the error. The module exists, that's the good news, but it can't load it. And so it gives you a hint on how to figure out how to load it. Unfortunately, it doesn't then do the hint itself. It just goes, now try module spider OpenMP. So we're doing that, module spider OpenMP. And that shows you all the available versions. So there's a couple of versions here. It still doesn't tell you how to load them, but it says, well, if you want to know that, why don't you try module spider OpenMP? It's kind of like, but you know, that's it. At least it gives you a hint on what to do next. So we start doing this next. Module spider OpenMP I311. It goes, yep, found that. Now you need to load these modules before you can do anything. So we're in business now. We have all the hints that we need. We will load. In this case, we will choose one of the two lines. So we'll choose the Intel one. So Intel, and then we can load OpenMP. So it takes a few iterations of spidering before you figure out what combination of modules get you where you need to be. But it's for the most part just sort of a single exercise. If you wanted to do NAMD, you go, okay, module spider NAMD, and it says, okay, I've got these versions. Okay, module spider NAMD specific version, it'll tell you, well, you have to load these compilers before you can load the module, something like that. And then you put that in your job script, and you're done. And just to check, do module list, and you see the Intel and the OpenMP are loaded. There's always this extra module that selected the tree. In this case, it was the 2018 Niagara and Mist tree. Okay. Is that kind of clear? It takes a little doing at first, but it's all meant so that people can run pretty much anything they want. Okay. Commercial software. We do get quite a bit of requests for that. We don't have any budget to spend on licensing, except for compilers, which kind of come with the system. So it's, paying for them isn't really what we do. And that's because everybody has their own favorite commercial software, and there's just too many different ones. So if you have a license for commercial software, and it is a license that allows you to run on a cluster, and that depends on the license and depends on the software, then you can make this work. And you probably want to talk to us and say, okay, I've got this license. How do I make this work? How do I get MATLAB to work? How do I get Gaussian to work? And there's different ways for each of them, because every commercial package is a little bit different. If you can stick with open source alternatives, that can be better mostly for scalability. A lot of these licensed software have a limitation on how many you can run at the same time. So if you have 1,000 cases to go through and you did it with MATLAB, you might run out of license tokens. You did it with Octave, you don't have that issue because there's no license. Anyway, these are possible, but always slightly tricky to get started. Python and R then. So I've talked about software modules. A lot of those are libraries or applications or compilers. Python and R are a little bit different. They don't fit very well within the module system. And so what ends up happening is that well, we have Python and R, and they're available as modules in different versions. And they tend to come with some packages. Python might come with NumPy and SciPy and Matplotlib and your standard stuff. If you need more packages, you will have to install it in your own home directory. It's very simple these days. It's a pip install or install packages in R. The only thing that you would need to make sure is to install these in virtual environments. And that way you could actually have kind of like modules, separate environments with different sets of packages if you need it. And so it works like this. You load the Python module. I'm loading Python 3 here. And then I create a virtual environment. The reason you have to do a virtual environment is if you try to install it without it, it will try to install in the system directories where you have no access to. So you basically can't. When you do a virtual environment, it makes a virtual copy of that that same Python installation without actually copying the files, so that's good. And then you can append more packages to it, but that lives in your home directory. So I'm creating a virtual environment called my env. I want to inherit all the packages that were already there, like NumPy and SciPy. That's what just system side packages does. That means you don't have to reinstall things that were already there. That creates the environment but doesn't activate it. So you have to activate it. That's how these environments work, by doing source. And then there's an activate script somewhere in the directory called myenv. Myenv is something you can choose. The rest is and then once you are in that environment, you can pip install anything you want, and it should work. Virtual environments are our preferred ways for users to move with their own environment. Very popular these days are Conda environments, which are way more powerful, and the power comes with a cost. They're not faster, they're just powerful, and you can do more things with them more easily. They add a lot of files to your home directory, and so before you know it, you're over quota if you've done like 2 or 3 Conda environments. And in many, many cases, what you need isn't all of that flexibility of a Conda environment. You just wanted a Python package. So your first try should always be virtual environments. It's almost always better. Only if there's some reason to do Conda. And I'll tell you, on the Mist system, a lot of packages only work with Conda. Not particularly like it, but that's how it is. But on Niagara, there's almost no need for Conda. So that's Python packages. If you have your own code to compile, no issue. We have compilers. We have GNU compilers, Intel compilers, OpenMP compilers. Just make sure that if you compile for the particular machine. Many build systems by default just compile for any old architecture, not the fastest way. So do something like -m arch native if you're doing GCC, or -x host for Intel compilations. If you need libraries, module spider them, they're probably there. I've given a small example here, loading the Intel compiler and the GSL library, and then just compiling a few files. But this is very detailed. But yeah, there's no issue in compiling code on Niagara or on Mist, really. There's more compilers on Mist for things like CUDA, OpenHCC, and other GPU-specific compilers. That's anyway. Yeah. So we have CUDA. In fact, on Mist, the first thing that you will load is the CUDA module, because everything is CUDA enabled. But without the CUDA module, nothing will work. At some point, CUDA will be upgraded. Right now, it's 10.2. It's the latest one. But we don't want to delete. We don't want to ever delete any modules, so that whatever you ran in the past, if you load the right modules, you can run it again. But that means that's why you want to be specific with like versions. But yeah, just module load CUDA, module load GCC probably for the host part, and then just compile your CUDA code. Testing. This is always a good idea before you blast your 100-node job into the queue. Test that a smaller scale version of it works, so that you don't wait for a day and you find out that after 1 second your job failed. Come up with a small test case. If it's a small enough test case, it takes a couple of minutes, a few gigabytes of memory at most, a couple of cores, or maybe 1 GPU on the Mist cluster. Just run it on the login. Just see if it runs. Because usually, if it is one of those, like in the first second it crashes, you'll see it right away. Right? And if it runs, great. You Control-C it, you break it, and you put it in a job, and fine. If it doesn't work, you want to debug it, we have the DDT debugger available in a module. So that's a parallel debugger, graphical debugger. It's kind of nice. We're working on getting it working on Mist. It works on Niagara. You can also profile. So if you're doing profiling or debugging, look into these two guys. They're in the DD2 module. Now, suppose you have a short test, but it doesn't fit on a login node. Say it crashes only when you use 100 gigs of memory. You can't run that on a login node. There's too many other people doing things. You can request for a very short time a node that's just dedicated for yourself. So you get one of the compute nodes for, say, an hour, and you can do whatever you would in a job. Use all of the RAM, all of the cores. That's fine. And because it's a short time, these are set aside, and they have fast turnover. So almost always when you ask for one, you get one within a few seconds. How do you get one? We have a command for it, debug job. So debug job n asks for n nodes. You can ask up to 4 nodes. Every node for Niagara has 40 cores, so you can ask up to 160 cores, which gives you should be plenty to do debugging. Like even parallel code should be fairly debuggable on that. On Mist, we schedule not so much by node, but by GPU. So you ask for a certain number of GPUs. So the debug job command is the same, but you give a -g and a number of GPUs. Often, your test will need 1 GPU, and you just go debug job -g1. Even if you leave it out, it will give you this one. And then for that, I think on Mist even we extended it to out. So you can just see why your CUDA code isn't working. And if it's working, you spawn up the DDT debugger and you run it through there and you see where it crashes and stuff like that. Okay. So this is important because the next step is submitting to the job, to a queue. The system is busy and there's still people wanting to do more, so you'll be waiting. Like waiting is normal. And how long you wait depends on so many different variables. A lot of it has to do whether your group has an allocation. So if they got a certain allocation, they get priority in the queue. Priority such that they can use their allocation. If they overuse it, their priority goes down. And so even if you don't have an allocation, you can easily run like some jobs. But once you've sort of gone over, but you get basically the leftovers. And so that is not little, but it means that when you've run jobs, other default users get to run jobs, and your priority goes down. There's a 1-week half-life of that priority. So the priority goes down depending on usage, but then that usage is counted by a factor of a half a week later, and another factor of a half yet another week later. So that basically, if you've used a lot in a week, you don't get too much done the next week. But the week after, you should be OK. That's kind of how it works. And that's how we even out that everybody gets a chance to use the system. And it also means that there's no cap. So if you have an allocation, say you have 1,000 core years in a computation, and by half of the year, for some reason, you've managed to use all of it up, it's not up. You can still run at the same sort of rate as long as there's resources available. A few things to keep in mind with the scheduling. So I'll give you how a job script looks like in a second. We schedule by node. This is meant for large-scale computations. If you don't have use for 40 cores at a time, you don't have to run on Niagara. You can either run on GPUs or on your own system. This is meant for that kind of scale. This can be 40 independent calculations that just run at the same time. That is fine, but it does have to have at least that scale. So because of that, we said we were just going to give whole nodes. And that does has a lot of advantages. First of all, your node is your node. There's no other user running on it and maybe exhausting the memory or writing to the local disk too much. If anything goes wrong with the job, you know it was your job crashing it. You have to debug yours. You don't have to wonder whether somebody else. So it also makes it's sort of a shielding. The only thing that is shared is the shared file system. Another thing we did is limit the wall time, so that how long your job can be, to 1 day. That might seem restrictive, but there's no way to schedule large jobs if you allow really long jobs. That one week long job can stop the 1,000 node job that you had to run for that whole week, and that is just not attainable. So we have to work with that. And the other thing is, and that's sort of a protection, or the other two things are, home is read-only. So home is backed up to be safe. We also made it impossible for you to write to home in your job. You have to write to scratch. There's no choice. That's where your output will go. It makes home nice and responsive. It makes the backup fast. It makes everything work well. But it is a little bit weird because your default job will think that it can write to home, and then you submit a job and it can't. It'll work right. Copying things to scratch and running from scratch is usually the easiest way to get around that. The other thing, the last thing that is typical and that's different from the jobs than the login node, no internet access. You can't download data on the compute nodes. If you need any data downloaded, you have to do it on the login nodes first and then submit your job. This also makes it harder if you have an off-site license server to contact, but there are some ways around that. Again, you'd have to focus that. But those are restrictions. So your job, it's very compute focus, if you can see. So you get your node, you know what to compute, your data is already there, and you just go and compute, and after it's done, you're done. Mist scheduling is by GPUs, which is so there's 4 GPUs per node. You can ask for a single one, then multiple single job node jobs will land on that node. But what we've done is, just to keep it simple, every node is carved in 4. So you get a quarter of the memory, you get a quarter of the CPU cores, and 1 GPU, and that's it. That's easy. If you need the whole memory, you have to ask for a whole node, and you get 4 GPUs with that. Just that's how it goes. So either single GPUs, or if you really have a large-scale computation for GPUs where you can use multiple GPUs on multiple nodes, which is still kind of a rarity, but it is the way to scale up, you can ask for a certain number of nodes. And then you get whole nodes, 4 GPUs in each of them, and nobody else is on those nodes. Use all GPUs, use all cores. We do monitor these things. If you see that you're not using GPUs on Mist, we'll send you an email and say, why don't you just go to Niagara? There's more resources there. You'll probably run faster. The rest is all the same. So no internet access on any of them. Maximum all time, home read only. So some restrictions. The debug job that I showed has all these same restrictions also. So if it works in a debug job, it should work in a job. That's that. That's it. Hyperthreading, I have to mention this because it's confusing. The operating system and the system itself pretends it has more cores than it has. So Niagara has 40 cores per node. You log in or you get your debug job and you see 80 cores. You go, how is that possible? It's double counting. It's a clever trick. It makes things faster on the average by pretending that there's 80 cores instead of 40, but it is kind of funny. And sometimes, occasionally, you have to say yourself, no, I just want to use the 40 cores because using 80 things at the same time is just too much. On Mist, it's the same, but the multiplier is a factor of 4. So the nodes have 32 cores. It will seem like you get 128. That's just the way you are. What you ask for, the cores you ask for, those are real cores. What you get are virtual cores. Okay. It usually doesn't matter too much, but it's something to keep in mind. It's fairly easy to use because you get a whole node. So you just do either 40 or 80, and it's all totally up to you. Skip on that. Okay, so let's look at a few job scripts. Here's a job script that I've called it OpenMP, but it means that it's running one task or one process, as they call. But within that process, it's using multiple cores. And using multiple cores in one process, it goes by threads. So each of the things that a core is doing, it's called a thread. So it's a multi-threaded job, and OpenMP is one way to program threads. That's why it's called OpenMP. So there's 2 parts to this kind of job scripts. There's a top part that has commands for the scheduler. It means what resources do I want. And then there's the bottom part, which says what do I want to run on those resources once I have them. So the resource request is 1 node. So dash nodes equals 1. Each of the nodes should have 40 CPUs per task. Slurm is really weird in how it calls things. This means 40 threads. Why it calls them CPUs, don't ask me. This is 40 threads. The time is 1 hour. I can give the job a name so that if I list a queue, I can find my job by name. I can tell it where to put output. If I don't, there's some default name, slurm dash some number. You might want to rename that. And you can get emails if something goes wrong. So if I say mail type equals fail, it will give you an email. Whatever is registered with CC, with your CC account, it will mail you that something failed. You can also have it mail you when the job starts, when it ends, depending on how much spam you want, so you can put it in there. And then that is a request to the scheduler. This is for the scheduler. So the scheduler will start looking for a single node with 40 CPUs. Well, they all have that, so that's pretty simple. For an hour, somewhere in the schedule, it's looking for a whole of one node by 1 hour, and the rest is sort of options. So we'll do that. So the first line is important, and it has to. Sorry, yes.
So for the output right there, this is what it'll write.
Yes. So
it'll name it that.
Okay, so person J is the number of the job. There's a few of these options.
Okay.
You can do man dispatch.
The
Yeah.
standard default.
That's right. So whatever would otherwise appear on screen goes into that file, right? Whatever you already write in files goes into those files. But right. So what I didn't talk about is this first line is important. You can only submit certain kinds of scripts, and bash scripts are the most common ones. You need this first line to say that it's a bash script. The lines with SBatch go to the Slurm scheduler. So scheduler is called Slurm. It reads those lines, and so what it goes looks for a node of 40 cores to run one task with 40 cores for 1 hour. If people weren't using this system all the time, you would find one of those nodes and start running your stuff right away, but it will probably put you in a queue, and at some point you're at the top of the queue. You have to submit this job from scratch because home is read-only. If you try to submit this from home, it'll go, hey, this file you want me to write to, OMP output, would live on home. You cannot write there, so we'll just basically not allow you to submit it. Submit it from scratch so you can write, and then it'll hang in the queue there for a little while. Once it's found a node and you're on top of the queue, it will then run this script. Now, for bash scripts, all these pound sign lines are just comments. So they just get skipped by what's run, and it just starts on this line. It loads the modules. The modules have to be reloaded. The way Niagara is set up, when you run a job, it's as if you logged into that node. So nothing is loaded yet. Your bash RC gets run, but as I already said, you shouldn't have any module load commands in there. So load your modules again. Again, this is also a documentation. These are the modules I intend to run with. If you ever see or look up an old job and you find your job script, you knew exactly what's happening. That's good. But if you don't load them, the thing will crash. For these particular OpenMP applications, you have to set an environment variable, OpenMP num threads, to make sure that it gets the 40 threads. Slurm sets a whole bunch of environment variables for you. On our documentation wiki, you can look up the examples. But in this case, you want CPU per task. And then you can run the example. So whatever this example should live in the directory that you submitted from, so that it can run, and that's it. Okay. So there's the resource, and there's what's run. I didn't say this yet, but this goes in one file. Say the file is called ompjob.sh, and then from the login node, from somewhere in Scratch, you type the command sbatch and the name of the file. Right. So I think the way R does it, it launches separate processes. So that's more like the next example I'll have. So yeah. So the next example, although it's called MPI, it's very similar. Here we don't have one process that is run, and in it the different cores do something. I have separate processes. But R and multiprocessing in Python do the same thing. It launches a new process, and so the number of processes, unfortunately, in Slurm is a different parameter. It's called tasks per node. So you would set tasks per node to 40, and then R can run with 40. And I'm not sure what it calls, 40 workers. Yeah, tasks per node. So this is an example where we use 2 nodes. That you don't have to. It's just one is perfectly fine if that's the scale at which you're computing. The rest is all very similar. I load some different modules in this case because it's an MPI call. If it is an MPI code, so that doesn't count for R per se, but it counts for code that runs across different nodes. You have to start us with MPI run, but those people that are doing MPI know that already, so they should be pretty straightforward. So it's all the same thing. The big difference here is that we're asking for tasks rather than CPU. Yeah, so this is the more common one, even for Python, those people doing Python and multiprocessing. Or if you're doing, if you have just serial jobs, they can only run one core, but you run them either in the background, you're 40 at the same time, or use an application like GNU Parallel, which can do that for you. And tasks is what you want because they're all different processes. If you have an application, and you didn't write it, but it says we can use threads, and then you go to the threaded examples for the OpenMP. Good. So we've submitted. After a while, it runs. It gives results. Maybe we've set it up to tell us when it's done by email. OK, but how do we keep track of these jobs? So there's a way to keep track of these jobs. A few ways. Once it's in the queue, you can ask for the whole queue. That's the sq command. It's a huge list that is completely useless because who cares that there's 10,000 jobs in the queue? You can't you could see where you are ranked in the queue, I guess, but that is really not that useful. You can just get your jobs. That is useful. So -u and then your username, because you can at least see that the submission was successful, and whether it's running or whether it's pending and whether it's waiting for resources, or whether it's not running because of priority, which means other jobs that have high priority are going to run first, which is fine. Eventually, that will switch from priority to resources and then to running. If you want to know a specific job, you can do -j in the job ID. So when you submit, it spits out a number, and that number is the job ID, and with that you can query the job. You can ask SQ to give an estimate for when your job starts. This is almost always wrong. Don't count on this. This will change as other people with higher priority submit after you. The only thing it will do is give you a very rough order of magnitude of how busy it is. Am I waiting for hours or am I waiting for days? And other than that, I don't think you could trust it at all. But it's one of the things you would like to know. You can't. You'd have to predict the future. You can't. A few other handy things to excuse me, to monitor your jobs as it's running. When the job is running, because it's by node, you can actually SSH to the node, log into the node, and poke around and see what it's doing, which is fine. We have also a utility, JobPerf, that logs in for you and figures out how much CPU it's using, how much memory. Eventually, you'll be able to do GPUs as well. It doesn't do that right now. So that's kind of useful. If the job isn't running well or hasn't run yet and you know you made a mistake, you can cancel it, cancel. You can cancel all of your jobs. Be careful with that. But you can do that. You can see if you're really curious, you can ask all kinds of things to the scheduler. You can say, hey, are there any nodes down? Is that why my job isn't running? As info.p. Almost always, when your job is not running, it's just waiting in the queue. It's very rare that it gives you anything, but you can snoop around. And if you have recently submitted a job, when it's finished, the saccount command can give you information on the job, like how much memory did it use, how much CPU did it use. But we have a better way to deal with job information than the command line one. So the better way is myscinet.ca. So this is a website. This is web-based. You log in with the same computer account. So here's the sign-in button. The front page gives you sort of the stats of Niagara, so how much is utilized. It's almost always around 98%. And the other percent are just waiting for jobs to start. How much of the scratch space is used, how much the burst buffer, how big the queue is. This is done in work hours. This is how much running. This is how much waiting. If you think about the scheduler being at most 24 hours, the way I interpret this is that I divide the waiting ones by 24, and that gives me an idea of the oversubscription of the queue. So typically, this kind of means in this case, there's about 300% oversubscription. Like if we had the resources, if Niagara was 4 times bigger, everything would still be busy. There's a lot of people, not a lot, but there are a few people that submit a lot of jobs that are just there, like, if they run, I'm fine. So the fact that there's so many jobs in the queue doesn't really mean that you're waiting for all of them. They'll probably have low priority. But what's really great about this is that you can log in and then get, for each of your past jobs, you get to see the job scripts, the environment it ran on, how long it ran for, the memory usage at every 10 minutes, the CPU usage at every 10 minutes, disk I/O. And so you can basically get a profile of your job. So here's an example of an MPI job that it's cut off a little bit, but ramped up from 50% to about 100% CPU usage. I can select here the memory usage. Sometimes you miss something in your estimate of how much memory you need, you run out of memory, you'll see that the memory available decreases and hits 0, and then your job crashed. It'll let you diagnose why this happened. This will also tell you if you have, say, a multi-node job, each node gets a dot, so you can see if all the nodes are really busy or not. It's a great diagnostic tool for your jobs if something goes wrong, and to see in the past. So here's a little zoom in. So it tells you what node you ran on. Here's the zoom in of the CPU usage. So obviously it started low, and then it went to 100%. That's great. That's what you want to see. It shows you the scripts, and this is exactly the script I showed in the slides. It shows you the environment. Yeah, so that's it. You can also see on my SciNet how much of your allocation you've used. If you have access to several allocations, which not a lot of people do, but if you do, you can see of each of the allocations how much they used and who used what. So it's a nice way to keep track of things. Okay, and then as I promised, I was going to end with some data management and I/O tips. So we have a shared parallel file system. The parallel means that we can write from several nodes at the same time with virtually no performance hit. And that's because in the backend, there's actually multiple drives running at the same time. And so you can do that in parallel. The file system is called GPFS. So sometimes we'll just complain about GPFS. It's shared, so it can be seen on all of the nodes. That's great. It's really tuned for high throughput, so rapid reads and writes of large data sets. It's not particularly good at many small files. And you can kind of imagine why. If you have a lot of nodes that are all trying to write at the same time, they have to somehow either let the other nodes know or have some central registry where they say, I'm busy with this file right now. It's kind of locked, or don't use it. So the more files you have, the more communication you need. Big, large files just need one communication, basically. So the little files are bad. Lots of files are bad. Big chunks written or read in consecutively, that's good. So keep the number of files small. Write in big chunks if you can. Write in binary. If you have numbers, write it in binary. They're faster, take less space. If you do have those heavy I/O nodes, as I said, we have an alternative, the burst buffer, which is better for heavy I/O. So just write to us, or there's even a temporary burst buffer for every job. You can start with that. You can also use memory if you want. And so slurm_temp there is actually the location of a RAM disk, which is so don't have many small files. And then finally, some more useful information or some links. Our main website, which has like stories. Niagara's documentation, which the most up-to-date one tends to be on our own site, but this one works as well. Mist, I don't think is there yet. You'd have to look it up. Other Compute Canada clusters are on their website as well. Our system status and all of the most recent documentation happens on docs.scinet.utoronto.ca. So I'll show that in a second. And training, as I always said, go to courses. If you have any questions, you email support@SciNet or Niagara at Compute Canada. They both will eventually lead to all of us, and one of us will answer you. If you need help, if you need one-on-one consultation, you need to get your stuff going, again, just email us. We'll set up a meeting and do that.